summary. Yeah, that should be fine. Yeah, the slides have been approved too. So awesome. Okay, so right. Quantum computing capabilities have grown tremendously over the past decade, and I think that's perhaps one of the reasons why many of us are even here. So it's a very, very exciting time for the field. We know that we haven't achieved universal fault-tolerant full-scale quantum computation, in part because of noise. And so this, of course, is not the only stumbling block, right? There are lots of challenges for full-scale quantum computation, but one of them is noise. And what I work on in particular is trying to figure out how we really can understand, grok the noise. This is the domain of what we call quantum characterization, verification, and validation, or QCVV. And what I want to talk about today are sort of the ways in which QCVV has been instrumental in advancing the field to where it is now, and hopefully will be continuing to be part of the story as we move forward. And of course, this is again just a small part of the story. I'm going to tell a small part of the QCVV story, which itself in turn is just sort of a small part of the story with respect to all the advances that we've seen in the field. So in terms of where are we now, here are just some high-profile papers that I'm sure people are familiar with. There was the quantum advantage paper from several years ago from Google, and of course there are some questions as to whether or not this is true quantum advantage, but it's pretty clear that this was still pretty impressive experimentally on more than 50 qubits doing random circuit sampling. This is, even if this is not true quantum advantage, you add a few more qubits, and in the very near future, we're going to have that. Of course, this is still on tasks that are in some sense fundamentally uninteresting, except for the fact that we think we can do them better on quantum computers, right? In terms of actual applications, people have been now demonstrating pretty exciting results on NISQ devices. So just down the street, for example, at IonQ, they've got some very nice results where they are able to show with about 30 qubits or so, being able to run some small scale algorithms. Of course, these are things that are, again, in some sense, not fundamentally useful insofar as these are tasks at this scale that can be simulated on classical computers, or you can just do the classical computation directly. And we have probably a pretty good reason to believe that NISQ hardware is not actually going to get us real sort of useful quantum utility. But nonetheless, this is still pretty exciting and pretty impressive results, right? And then from my perspective, at least, sort of the most exciting things that we've been seeing lately have been demonstrations of logical qubits and actual quantum error correction. So for example, this paper from the Harvard group from the end of this past year, of course, not the only one. So we're now seeing actual quantum error correction run on hardware, roughly at break even, give or take, depending on how you want to count it. But again, of course, still not at the scale at which we can do sort of real useful things, where we're demonstrating real quantum utility. But clearly this is, big improvement. A lot of progress has been made since where we were 10, 15 years ago, when most groups had 1 or 2 qubits to rub together at the most, as it were, and with relatively low fidelities. So what's taken so long? What's taking so long? Well, one of the big issues, of course, is noise. And again, this is not to discount the other challenges like scaling up and fabrication issues. But one of the issues just fundamentally is noise in quantum processors. And it doesn't matter sort of what your architecture is, what your hardware platform is, whether it's trapped ions or atoms or semiconductor spin qubits or superconducting qubits and transmons, or any of the other sort of more exotic platforms that are out there. Right? And this is because quantum information is fragile. We're talking about very small energy scales, very low temperatures, typically often a Kelvin or less. And of course, the qubits are very sensitive to the environment. So heat, light, vibration, other qubits, right? We want qubits to be able to talk to one another, to be able to entangle them. But then once we're done doing the entangling operation, we want them to not see each other. And of course, that can be very challenging to control properly. And so what does this lead to? Among other things, you have very quick decoherence time, right? So for example, you consider a transmon platform, a typical T2 time for those sorts of qubits are about 100 microseconds, and gate times are about 100 nanoseconds. So if you ask, well, how many gates can I perform before I've completely lost the coherence? About 1,000 gates, right? So imagine that your laptop, you turn it on, you got 1,000 clock cycles before blue screen of death. You wouldn't be able to get very far. So in terms of how does this compare to classical hardware, right? If you consider the transistors in your laptop, they've got an error rate of about 10 to the minus 28. You go back 70 plus years to ENIAC, even those vacuum tubes had failure rates of about 10 to the minus 15, 10 to the minus 16. Right now with quantum hardware, 10 to the minus 2, 10 to the minus 3 on good platforms, some really good ones, 10 to the minus 4-ish, depending on how you count it. We think maybe if we're really lucky and experimentalists are very clever, we could get to 10 to the minus 5, maybe even 10 to the minus 6, but that's probably a stretch, right? That's a huge gap between what we have with classical hardware and with quantum hardware. And where do we need to get for quantum application needs? Even if we don't need to get to 10 to the minus 16, we need to get to at least about 10 to the minus 10. So of course, we're going to use something like error correction, right? And again, this is all, I'm sure, the review for everybody, but just in terms of what we are, the plan here, of course, is we're going to use error correction. If you're below some threshold or a pseudo threshold, you're going to be able to suppress errors, right? And so the most general threshold we have is 6.7 times 10 to the minus 4 in diamond norm, as it turns out. There are sort of better thresholds depending on the precise code. But no matter how you slice it, we think you're going to need, oh, sorry, question, yes. And please feel free to ask questions in there. Great. So pseudo threshold, so when we talk about the threshold of a code, right, this is not for a specific code, say like at a fixed distance, it's for a family of code when you look at the infinite distance limit, right? So the pseudo threshold is for a particular instance of a code at a fixed distance, the error rate below which the logical qubit's going to have a lower error rate than the operations on the physical qubit. Does that make sense?
Break even.
Break even, yes, for a particular instance of a code in a family of codes. So we're going to need a bunch more qubits, and we're going to need lower error rates, right? So we ask, well, in the meantime, before we have actual useful quantum computers, how do we analyze the performance of these devices? It's in some sense sort of a little premature to have traditional benchmarking suites in the fashion that you have for classical computers, something they say, LinPack. It's too early for quantum LinPack because we don't have a quantum linear algebra, for example, that we can do that's actually useful. But we can still assess the performance of quantum computers. And in general, we sort of break this down into two separate categories of tasks. We have what we call characterization, which is just the full description of quantum operations. So for example, writing down the process matrix. I'll explain a little bit more what I mean by that in a moment. And then there is what we consider to be or called benchmarking. We're asking sort of how well the quantum hardware performs on performing certain tasks. And so the analogy that we like to think of is, imagine you've got some race car, right? And you take it into the shop and you examine every single component, all of the little nuts and bolts and objects inside the car, and you have some nice model that tells you, okay, now I know how fast the car will go on the track. That's characterization. Benchmarking, you just take it on the track and see how fast you go. And of course, if you don't have a perfect model, there's going to often be some disagreement between the characterization and the benchmark. When we talk about QCVV, quantum characterization, verification, and validation, this is sort of the subfield of assessing the performance of quantum computers. And in particular, we think about characterization as benchmarking as being sort of the two main subtasks that fall under QCVV. And in particular, today, I'm going to be talking pretty much mostly about characterization, but there's a whole lot of interesting work that's done on benchmarking as well. So in particular, I'm a member of the Quantum Performance Laboratory at Sandia National Labs, and what we work on in particular is QCVV, assessing the performance of quantum computers. And so we try to come up with novel ways to characterize qubits, to understand their performance, to figure out how to make them better. And in particular, we seek to do it in a framework where we're just looking at the execution of quantum circuits and analyzing the corresponding output. So we're mostly physicists, but the actual underlying physics is mostly abstracted away. We want to sort of, in some sense, be doing physics without units. We want to be talking about quantum computers in a way where we've abstracted away the particular physical details, whether you're talking about a trapped ion platform or superconducting platform, not just so that you can make comparisons between them, but so that you have some sort of unified framework in which we can understand the performance of these devices. So if we want to actually improve quantum hardware, we need to understand the behavior. And in some sense, this is isomorphic to the notion of being able to predict the output from quantum circuits. So sort of the framework that we have, you imagine that your quantum computer it's just some black box, and you've got buttons that you can push on it. You've got a button for state preparation, you've got buttons for gates that you push, and you have a measurement button that you push at the end, and then you get a light that comes on to tell you, do you get a 0 or a 1? Or you have a string of lights to tell you for multiple qubits, right? And you're just going to be running quantum circuits in this sort of paradigm. And so the framework that we have for characterization is you have some collection of circuits that are chosen in some intelligent fashion. You perform them a bunch of times, you record the outcome frequencies, and from those frequencies, you're going to infer some sort of hardware model. And what do I mean by a model? Just something that's going to map circuits to outcome probabilities. You can then evaluate the model quality. You ask yourself, the prediction that the model makes for the circuits that I happen to have run or that I run afterwards, how well do they match the observed frequencies? And if they do a good job matching them, you've got a pretty good model. And if not, well, then you don't. So in some sense, again, we've abstracted away the physics. We want to learn about what these button pushes actually do, right? So what we're doing here is we're pushing buttons to learn about buttons. What does this mean sort of mathematically? So I imagine this is probably review for most people, so my apologies. But in the ideal picture, you have some pure state psi that's going to experience some unitary evolution when you apply some quantum circuit to it. And then you apply a measurement and it follows Born's rule, right? This, of course, is not actually how things work in practice. In reality, you have some noise, some classical noise that the system is going to be subject to. So instead of describing our system with some state vector, we're going to describe it with a density matrix. And I have a little die here on the side to remind us that what we're really doing in some sense is you can think of, you've got this little black box, you push the state preparation button, and you've got a little gnome inside who rolls a die with some probability distribution, and according to the outcome on the die, outputs some particular state. You don't know what value the die took when the die was rolled, so the best description you can give for the system is this density matrix. If you know the probability distribution of the die that is being rolled, you can describe the density matrix. Similarly, for state evolution, for the actual gate operations, we no longer have unitary evolution. We have some collection of Krauss operators, right? And these Krauss operators, not always, but in sufficiently nice cases, correspond to various unitary operations that have some probability distribution associated with them, just like we had for the state preparation. So again, you roll a die, you see what what the outcome is, and then you apply the corresponding unitary operation. You can also generalize this for non-unitary noise if you have things like amplitude damping, right? And then measurements can also be noisy, just like state preparation. You're still going to follow Born's rule. So when we talk about full noise characterization, we mean to say, I want to be able to write down all of the elements of a gate set, of all the buttons that I can push, the density matrix for the state preparation row, the process matrices for these Gs, and then again, some matrix for this M. So we're learning the gate set. There's one small problem sort of in terms of how we want to write these things down. If I want to just use sort of the standard Krauss operator formalism, this becomes very messy very quickly, right? I just have a whole bunch of sums of matrix, matrix, matrix multiplication, and this just becomes a little bit messy to keep track of. So there's a pretty simple, straightforward thing we can do. And I see, by the way, there's some comments in the chat, but I can't see what they are. I don't know, anybody have any questions in the chat? Or these? No. Nope. Okay, cool. Okay, right. So we're going to. Excuse me?
It's a comment in chat, more of a comment than a question. Nice cow.
Oh, yes, yes. So the cow. This is right. This is my spherical cow, because indeed this is all of this is still sort of a spherical cow model. Even what I've described here in the green box, I have assumed that we have perfectly static gates, that things are Markovian, and I'll talk a little bit more about that later as well. So thank you. Okay, so right. Yeah, in terms of the mathematical formalism, we're going to just go and vectorize our density matrix. And what does this mean? I can represent my density matrix now here in the right-hand side. I'm going to put it in sort of a double-angled ket, or what we call a super ket. And the elements of this vector are now just some normalized block vector elements. In fact, these are just expectation values of all of the different Pauli operators. And we have the trace at the top as well, which should just be 1. And in this framework, we can now evolve the density matrix just by matrix multiplication. So our gate operation, which was previously described by a collection of cross operators, can instead just be a single matrix. And so now we've turned the problem from matrix multiplication into just matrix vector multiplication. And so this is pretty straightforward to do. We call this matrix G a super operator or a process matrix. And I know that it's CPTP, or completely positive trace preserving. So this is sort of a generalization of unitarity. It means that we preserve the trace, right? So we're always preserving probability, and it's completely positive, which means that any input state that you give, even if it's entangled with some larger system, you're always going to get out a valid PSD, but positive semi-definite density matrix. Okay, so we have matrix multiplication now to just describe the evolution of the state. And again, Born's rule, there's the simple generalization of Born's rule to describe the system. So now we ask, how do I actually learn what all the button pushes do? So there is sort of the standard textbook approach of tomographies. We start with this notion of state tomography, right? I have some density matrix rho, which I'm going to now just describe as this vector. And I say, all right, I want to learn a vector. How do I learn a vector? I learn its components. So the components here are just expectation values of Pauli operators. So I have my unknown state. I'm going to just do a z measurement a bunch of times to learn trace of z rho, and then the same for the x basis and the y basis. So I just do z, x, and y measurements, and I'm going to learn the density matrix. First, there's a sort of a small problem with this, which is I need some pre-calibrated measurements, and I need some pre-calibrated gates to be able to perform the measurements in the basis, in the various bases. So, okay, well, how do I go and make sure that I've got properly pre-calibrated gates? I'm going to do process tomography, where I take my unknown gate and I sandwich it in between some informationally complete set of state preparations, some informationally complete set of measurements, and I can learn those gates. Those, of course, rely on pre-calibrated state preparations and pre-calibrated measurements and more pre-calibrated gates. So this is sort of hopelessly circular in some sense. What we need is some form of calibration-free tomography. And so one particular protocol, not the only one, but one of them that solves this problem is called gate-set tomography, or GST. So I'm going to talk about next. And so there are a few different flavors of GST, but the simplest one is what we call linear inversion gate-set tomography, or LGST. And so you can think of this as, again, just a calibration-free process tomography. What we're going to do is we're going to consider all of the different state preparations that we want and all of the different measurements that we want. And each one of those is going to correspond to some small subcircuit that's going to emulate a particular measurement or prepare us in some particular basis. And we call those subcircuits, we just call them fiducials. Okay, so I've got some preparation fiducials and some measurement fiducials. And I'm going to take all the gates that I want to characterize and sandwich them between all possible state preparation fiducials and measurement fiducials. So I have this particular family of circuits, and this is identical to process tomography, right? Then what we're going to do is we're also going to characterize sort of just the empty operation. So I'm going to do tomography. I'm going to tomograph the empty operation. That's this second set of circuits that we've got here on the right-hand side. And critically, what I need to do is any gate that appears in the state preparation or measurement fiducials, those have to be characterized, those have to be tomographed as well. Now I've just got some collection of experimentally observed frequencies, and I can just turn a linear algebra crank. I just basically compute a matrix inverse, and I can compute an estimate of the gate set. So it's now done in some informationally, it's done in a internally consistent way. We've solved the pre-calibration problem. So it's okay if we haven't precisely prepared, say, a plus state or a y plus state or a z eigenstate. So there's a cost to doing this, though, and that is what we call the gauge degree of freedom. So effectively, when we say we don't know what the bases are that we are preparing in precisely, we don't know the bases in which we are measuring precisely, we don't know sort of what our frame of reference is in some sense. So you can imagine taking your gate set and picking your favorite invertible map B and just applying it to all of the elements of your gate set. This will not change any observable probability, any observable frequency. It does not change any observable of the system. So all of a sudden we've got this equivalence class of gate sets that are all equally consistent with the data that we've measured. So it's a little bit of a problem, right? Because you want to say something like computer fidelity, ask how well have I implemented the gates on my hardware? You need to be able to actually compare against some sort of gate that has, you know, expressed in some particular frame of reference. So it turns out this is a relatively easy problem to solve. You do what we call gauge optimization. You just can optimize numerically over the set of all possible invertible maps, looking for the gate set that is gauge equivalent to the one that GST has returned that is closest to your target gate set. And then you can go and reasonably compute your metrics. So in terms of what we get next after that, you know, so we've solved that problem. There's still some problems that we have. Oh, question, yes.
So you're saying minimize is the difference between the gates that you want to implement and the gates that realize with any of these?
That's right. So you look over the set of all invertible maps B, and you minimize. In particular, we compute the Frobenius distance, but your favorite metric between the estimate of the gate set and the target gate set. And so you're looking basically on an orbit of all gauge equivalent gate sets. So they're all physically the same.
How's that not just wishful?
Excellent question. Yeah, experimentalists ask this all the time. So in some sense, so the analogy or an analogy is if we say, okay, imagine I've got, you know, sort of a perfect gate set, okay, and I say, all right, here are my X rotations and here are my Y rotations and here are my Z rotations, and the experimentalist says, no, you got your X and Y backwards. I have a different handed coordinate system that I use, right? It's perfectly about, oh, okay, we're just gonna switch the coordinate system. That's effectively what we're doing here. The predictions of the gate set don't change under gauge transformations, right? So there's nothing physically observable or predictable that changes when you do a gauge transformation. So if you have lousy gates, so for example, suppose you've got a lot of decoherence, right? That's going to change the eigenvalues of your gates. The eigenvalues are gauge invariant. So you do this gauge transformation and you're still going to be stuck with some amount of decoherence. You can't make that go away. Does that help?
So it sounds like and the answer is well, since this is a gauge freedom, what choice we make doesn't matter.
That's effectively right. So we're going to make the one that is most useful for the experimentalists. That's an excellent question. So a remaining challenge is that this is not a particularly efficient sort of characterization procedure. We're limited in accuracy by the standard quantum limit. So our accuracy scales as 1 over the square root of the number of counts, the number of shots that we perform in the system. And we know, of course, that there are characterization techniques that go at the Heisenberg limit, where instead of getting something that goes as 1 over root n, we can get things that go as 1 over n or comparably. So we're going to leverage some known tricks from Heisenberg limited characterization procedures to be able to actually go and achieve the Heisenberg limit. In scaling, so we're going to get a much more accurate, much more efficient estimation procedure for our gate set. And the trick is to use, oh, yep.
So maybe we're just about to answer this question, but I usually think of achieving the Heisenberg limit by preparing some resourceful entangled state.
Yes.
So how do you have that if you don't know how to build it yet?
So it turns out in this particular approach, you don't need some entangled resource state. You can instead get, and we'll see here, you can achieve this through the use of short repeated sequences to, instead of, this is like a space-time trade-off in some sense. So instead of having some like big GHZ state, where then you apply your gate a bunch of times in parallel and you get like buildup of a phase, we're going to apply the gate a whole bunch of times sequentially and get that same sort of phase buildup. So excellent. Right, we want to be sensitive to small errors. So imagine that I've got some gate that implements some small rotation, some small z rotation by some amount theta, and theta is significantly less than 1. So I can push my gate button that corresponds to this operation, and I can do some small amount of rotation. if I want to distinguish this operation from identity, or I want to learn theta, I'm going to need on the order of 1 over theta squared measurements to distinguish from identity, right? So that could be a lot. Alternatively, suppose I just push the button, say, on the order of 1 over theta times. Now I've gone all the way to the other side of the block sphere, and with very few measurements, I can distinguish this operation from identity. So I can amplify coherent errors through repetition, right? So this is the cost is more in time instead of in space, right? Instead of using an entangled resource. So of course you might ask, well, wait a second, how do I know how many times I should repeat the gate? I said do it, 1 over theta times, and you don't know what theta is. So of course, what you then wind up doing is you sort of proceed iteratively. You're going to push the button once, you apply the gate once and do some measure and measure. Then do it twice, then 4 times, and so on. So you sort of bootstrap your way along, and then you can learn the phase to high accuracy. This is very similar in some sense to a protocol like, say, robust phase estimation, if you may be familiar with that. So we say, well, can I just do this to learn all of the gates? I just take each gate and then say do tomography on repeated powers or logarithmically spaced powers of the gate. So it's going to tell us some of the information about the gates, but it's not going to tell us all of the information. There's going to be relational information about the gates that we don't learn by just repeating the gate a single gate multiple times. What I mean relational information, I mean things like errors that you can't see by looking at a single gate, but you can look at by looking at gates collectively. So suppose you've got an X rotation and a Y rotation. Not only do we care about the rotation angles of those two gates, we care about the angle between those two rotation axes. And the only way that we can learn about that rotation axis is by doing something like taking some product of those gates and then repeating that many times. And we can then learn about the relational errors as well. So we're effectively turning eigenvector information from the gates gx and gy into eigenvalue information about this product gx, gy. So this leads to what we call long sequence GST, and it's more or less just basically what I've described. What we're going to do is we're going to form up a collection of these small subcircuits. We call them germs. Is there a question?
Oh, sorry.
Yeah, sure.
Like you start by talking about like the process matrix or superoperator kind of error. Like, am I understanding correctly here? This sort of using error rate only applies for like static or coherent errors. Like, would it work if you have just decoherence?
Sure. Yep. It'll absolutely work for decoherent error as well, because so instead of the vector going around, it's going to shrink,
So
right?
What sense is like the assurance like? How can I think of it as a Heisenberg limit? Like, what is it compared to? Like, I guess it's the kind of there's no like when you talk about Heisenberg limit, like in what kind of context? Do you want to think of it as a Heisenberg limit?
So I think this is a very good question. I think in some sense it is probably sort of more accurate to say that this is Heisenberg-like in some sense. You're going to be able to get amplification up to 1 over the decoherent, right? Like you've got some decoherence rate epsilon. Once I've applied my gate more than 1 over epsilon times, then I'm not going to be able to distinguish this from just uniform. So there is a cap on it as a function of the strength of the decoherence. Absolutely. So in order to learn the gate set, right? So we're going to just now do GST experiments or do effectively process tomography experiments on all of these short subsequences that we call germs that we have logarithmically spaced powers of or repetitions of, in addition to the gates themselves. And so one of the tasks is to then select a collection of these germs that are what we call amplificationally complete. We want to cover sensitivity to all of the parameters in the gates, and there's fairly straightforward ways to do that. And once you've done that, you can now run these long sequence GST experiments, and to actually learn the data, you can no longer just use linear inversion. You have to have you have some likelihood landscape that's got to have a whole bunch of multiple maxima in it, and so you use some sort of maximum likelihood estimation where you sort of bootstrap yourself along from generation to generation, a number of repetitions. You repeat the gate once, and you come up with the germs once. You come up with some sort of very coarse-grained estimate for the gates, that you use that to seed the optimizer for the next round, where you're now trying to incorporate the data from the germs repeated twice, and so on. And you can learn the gate set now with the Heisenberg limit, again up to decoherence, where instead of learning at 1 over root n, you're learning at 1 over L root n. So you can very quickly learn the gate set to high accuracy. And so we're using MLE methods, but we're looking at other methods as well for like online learning. We're looking at some Bayesian approaches, things like the Kalman filter. I'm not going to talk more about today, but these are things that we're also looking into. So it works insofar as, you know, we've convinced people to use it, which is nice. And here are a non-exhaustive list of some papers where people have performed GST. So we're collaborators on some of them people have used independently. This is available in our open source software package Pigsty. It's pretty simple, pretty straightforward to use. So this is nice, but how does it actually help make systems better? Right? I was saying at the beginning of the talk today that we're going to be talking about protocols that are actually just being used to improve the performance of quantum hardware, right? So how do we actually use GST in some useful fashion? So what do you do once you've done GST? Well, there are a few different things you can do, you know, whether you've done GST or just have an estimate of the gate set through your favorite estimation protocol. So you can compute metrics, right? You can compute something like the infidelity or diamond distance. And this is nice for splashy papers, for high impact, high profile papers. It's good for satisfying funding. You say, oh, look, we got another 9 of fidelity. That's nice, but this isn't like a great diagnostic tool, right? If I tell you the fidelity of a particular gate, it doesn't tell you what's going wrong with it. It doesn't tell you how to actually go into the hardware, into your control hardware or into the actual physical chip itself and make things better. So the things that we can do that are actually going to be really useful in some sense. The first is we can just verify that the model estimate fits the data. Is our understanding of the system as a collection of CPTP maps, is that correct? And if it's not, what can we learn from that discrepancy? And then what do I do with these process matrices? I've got some collection of numbers. Is that actually useful in some sense? What do I do with that? So let's look at the second thing. First, we'll look at verifying the model estimate fits the data. And so we can imagine, sort of by analogy to imagine you've got some collection of data points in the picture on the right here, and you say, I want to fit some linear model to it. Is described by some linear model, and you throw down the line that best fits it, and you've got a bunch of points that fit, but then you've got some outliers. So wait a second, this is not actually described by some linear model. That's very much sort of what we're doing here, right? And why might the model not fit the data? Well, in particular, we have some notion of what we call non-Markovianity or non-Markovian noise. And unfortunately, this is sort of an overloaded term. Many people use it and mean many different things. So I'm not going to advocate for one being sort of the correct term or interpretation, but I'll tell you what we mean by it. We mean specifically not Markovian, whereby Markovian, we mean that the dynamics described are temporally static CPTP maps. So let's say you push a button and it applies a particular process matrix, and it is always going to apply that same process matrix no matter when you push it. So there's no leakage. It's going to be of the appropriate size. So we don't need some larger process matrix to describe the dynamics. There's no drift. So there's nothing varying temporally. You have most forms of crosstalk are forbidden in the Markovian model. I push a gate to do push a button to do a gate on qubits over here. It's not going to affect qubits over here. I don't have other sorts of context dependence or other sorts of memory. So if I apply, say, a CNOT gate, then that doesn't make gates that follow it any worse. So this is sort of what we mean by Markovian, and then non-Markovian is anything that is not that. So how do we check to see if the model fits the data? Well, we did some maximum likelihood estimation, and you can then just compute a log likelihood ratio based on your estimate. And you're effectively just sort of looking at the discrepancy between the observed frequencies from your data and the probabilities that your model predicts. And so if the null hypothesis is true, that is to say that you've actually successfully fit the data with an appropriate Markovian model, then this log likelihood ratio is going to be it's going to be a chi-squared sub k distributed random variable, where k winds up being sort of the number of degrees of freedom that you've got in your data set minus the number of degrees of freedom in the model. So you can now compute some notion of n sigma, the number of standard deviations for the random variable, sort of how unexpected is it to see some log likelihood ratio of that particular size. This corresponds to a p-value. So in the same sense that when particle physicists talk about sort of a 5 sigma event, that's exactly what we mean here when we talk about n sigma. And so in general, sort of rule of thumb, we say if n sigma is significantly larger than 2, or the p-value is significantly less than 0.05, we're going to be careful we don't have a p-value hack, of course, then this is some signature of non-Markovian error. So this doesn't mean necessarily that if you've got a large amount of model violation, that there's a lot of non-Markovian error in terms of effect size, but it means that we're very confident that there is non-Markovian error present in the system. So in terms of using this for actual diagnostic purposes, we can also compute per iteration and per circuit log likelihood ratio. So, we've got these generations of the GST data where we've got repeating the germ once, then twice, then 4 times, and so on. So for each one of those generations, we can compute a log likelihood ratio. And then for each individual circuit, we can compute a log likelihood ratio as well. And then we can introspect the amount of log likelihood, or the amount of model violation we see sort of in the full data set to try to get a better handle on certain forms of non-Markovian error that might appear. So to give you an example, here is some data, here's some analysis of some data that we took on a trapped ion platform at Sandia as a single qubit system. And the top, we've got amount of model violation measured by n sigma as a function of the number of repetitions of the germ, of the germs. And we see that as we go out in circuit depth, we get more and more and more model violation. We are more and more certain that there's some non-Markovian error present. And then we can introspect further. We can actually look at each individual circuit. So what I've got here on the bottom is a little plot that corresponds, each pixel corresponds to an individual circuit. It's organized on the x-axis, again, by approximately the circuit depth, the germ repetition number. And on the y-axis, we've got the individual germs. And then each little plaquette corresponds to, on one axis, we go through the different possible state preparations, and on the other axis, the different possible measurement bases that we can use. And if a circuit is in model, it gets a sort of a white or a gray dot. And if it's out of model, it gets a red dot. And so we see here that, oh boy, there's a lot of non-Markovian error, but in particular, it's sort of restricted in some ways where it shows up. There's some nice structure, right? We see that it gets bigger as we go. And in particular, if we look closely, it shows up in circuits that contain the idle operation. So this is where we're characterizing here an x pi over 2, y pi over 2, and idle gate set. And so it turned out that the idle operation, sort of surprisingly, led to a lot of non-Markovian errors. This is kind of surprising in some sense. Idle, that should be pretty easy. You just don't do anything for one clock cycle, but somehow this is causing problems. And so the solution that the experimentalists came up with is, let's do some dynamical decoupling. Let's, instead of doing idle operations, we're going to repeat. We're going to say an x pi over 2, y pi over 2, x pi over 2, y pi over 2 gate. So this will give us a composite idle, and let's see what happens. So they implemented this, and all of a sudden, the non-Markovianity has gone away. So they've now been able to make the system very nicely behaved in some sense. It turned out, sort of interestingly, we wouldn't learn for a little while. It took us a bit longer to learn what was actually causing the error. And it turns out that for this particular platform, the way that the gates are implemented is you've got some microwave horn that's just blasting the chip that has the qubit with some microwaves. And when you want to do an idle operation, you turn the microwave horn off. Of course, the way you actually turn it off, you've got some attenuator that you turn on, so it's electrically activated. And that's going to attenuate by, say, like 60 dB the actual signal. It turns out that what was happening was that when you turned that on and off, there was some ring down effect on the microwave after you turned the attenuator back, turned it off. So you want to do a microwave gate, an x pi over 2 gate, for example, after you've done an idle. Once after getting some nice sinusoid, you've got some weird ring down, which means you've got a context dependence. It means that every time you do x gates after idles, for so many x gates, so many clock cycles afterwards, you're going to have sort of worse x gates than you otherwise would have. So this is, interestingly enough, something GST didn't tell us, oh, you've got ring down in your attenuator or in your microwave source, right? That's using more physics. The experiments need to introspect more to understand what's actually going on with the platform. But this pointed in the direction of saying, something is weird with the idle. So this is just sort of one example of how we can sort of use this information diagnostically to make the platform better. So I want to now talk a little bit about how we actually understand the process matrices. And for that, I want to talk about a different experiment that we collaborate on. This was with the University of New South Wales, where they've got a semiconductor spin qubit platform, and we looked at a 2-qubit system now, where we're looking at X and Y pi over 2 gates and now a controlled phase operation as well. And here is, for example, the GST estimate of the process matrix for one of their X pi over 2 gates. So let's interpret this process matrix. Process matrix, what does this mean? This is just, some array of numbers here, in terms of how you actually like interpret what the colors are here. So green is supposed to be positive and yellow is negative, and the little wireframes are the targets. But if you know this array of numbers, you hand this to an experimentalist and say, this is what your gate is doing. This is not very useful in some sense. Okay, I can deduce, there's a little bit of decoherence because I can see sort of ways in which population is getting suppressed, but this is not that helpful. So what we're going to do is we're going to use what we call the error generator frame. And the model that we have for this is, you say, imagine that your noisy gate is a perfect gate, some gate G0, followed by some error man. Okay, so you have a perfect gate followed by a noise channel. This, of course, is some, again, spherical cow approximation, but it turns out that it works pretty well in practice. And you can then say, all right, now the actual error channel is going to be some e to the L, where L is just some Lindblad operator. Okay, you've got some 240 parameters, that the degrees of freedom in your model for a 2-qubit gate. You can learn what the error generator, this Lindblad operator, is, just log of G0 inverse. Now you got another matrix of some numbers that are still, not necessarily terribly useful, terribly helpful in terms of explaining, what's going on. But what you can do now that you've got this particular quantity, this particular map, you can project it. You can compute inner products of this map with different sectors of actual specific noise channels. So you can consider, what are my stochastic errors? What are the Hamiltonian errors? And then in particular, what are the stochastic errors in the xi direction, corresponding to, just randomly having some x gate occur? Or alternatively, in the Hamiltonian sector, I've got some iz error, so I've got some z rotation, right? And when you do this, for this particular gate, a couple of nice things sort of fall out. So first of all, it turns out there are only 10 significant parameters instead of the whole 240 of them. So we don't have a whole lot that we have to consider in terms of understanding what's making the gate go bad. And it also turns out, conveniently, most of the errors are Hamiltonian errors, which correspond effectively to things that are easy, quote unquote, to fix. And what I mean by that is, these are things that we can typically fix just by changing the calibration of the pulses, or the pulse duration, or the pulse shaping. Stochastic errors often correspond to things like, fabrication errors, or you might have some sort of 2-level systems that are in the device. Those can be sort of much harder to fix, short of going in and refabbing the device. But even then, it's, you can get some sense of what are the rates at which these particular sorts of errors are happening, and what kinds of errors are you particularly prone to? What are the things that are really messing up your system? So, you can see here all of a sudden, most of the errors Hamiltonian. Most of it can be calibrated away. Or at the very least, if you say, I don't want to do any new calibration, you can apply some methods like, say, randomized compiling, which I'm not sure people are familiar with, but the idea is that you just, by using certain random gates to compile the actual circuits you want to run, you can quadratically suppress the impact of the Hamiltonian, the unitary errors. So there's something else that was also very interesting that we noticed in this particular experiment. We found in all of the local gates between 1 to 5% ZZ Hamiltonian error. This is pretty surprising. And the reason why is, these are local gates. We don't expect any sort of entangling operation, any entangling error, any sort of crosstalk to show up, because of the particular nature of these qubits, right? These are some donor qubits in one of these semiconductor heterostructures. We're now talking about the actual physics, where physics is not abstracted away, so we're far outside my area of expertise. But I am told that in these sorts of systems, you should not be able to have entangling operations, entangling noise between the qubits. This is not like, say, for example, a transmon platform, where you very frequently will have some small amount of ZZ coupling between adjacent qubits. And so the experimentalist said, this can't be happening. We can't have this sort of error. What's going on? And we said, well, let's go and check our code, check the analysis. We checked it a whole bunch of times and found no errors. And finally, working with our colleague Andrew Bashevsky at Sandia, who's a device modeler theorist, he figured out the answer. Problem with the attenuator again. So again, you've got an attenuator that is present to turn off the electron spin resonance pulse, which is what's used for the CZ gate, the actual entangling operation. Again, supposed to be 60 plus dB of attenuation. Turned out that it wasn't actually that good in terms of the attenuation. Some ESR pulse, ESR power was leaking through. And so what that meant was during every single local gate, you're still doing some small amount of CZ. And what is a CZ gate? Well, it is up to local unitaries. It's just a ZZ interaction. So that's what's going on, what was going on in the system, and they were able to see this and can solve this problem, and now all of a sudden make the platform significantly better. So these are the kinds of error mechanisms we seek to find and correct with QCVV. And going back to what I was talking about at the beginning of the talk, GST has been used in some platforms that have had some very nice high-profile demonstrations of really advanced hardware. Other protocols are used on other platforms. So this is not, I'm not saying that this is the only one out there, but this is one of the ones that is, I think, particularly sort of useful and helpful. So sort of, running out of time, I'll make sure we leave time for questions, but just in terms of things I didn't get to talk about very, very quickly, it turns out, of course, that GST is pretty expensive from an experimental perspective. We're talking about, say, 10,000 circuits if you want to do a reasonable 2-qubit experiment. This is very expensive for most experimental platforms, but it turns out that there are some very nice ways that we can go ahead and make the experiment design significantly smaller. We can leverage the fact that these are massively overcomplete experiments where you are performing many more circuits than you have degrees of freedom in the model. So you can intelligently sort of figure out what are the circuits that we don't need and throw those out. We've got a couple of papers on that. We can reduce a 2-qubit GST experiment from about 10,000 circuits in size to about 1,000. We can also use reduced models. Instead of saying I need an exponential number of parameters to describe the system, going back to what we saw a few slides ago, instead of needing 240 parameters, there were about 10. It turns out that in particular, when you go beyond 2 qubits, you've got, you need 4 to the n. You've got states that are of size 4 to the n. Well, it turns out that in terms of the errors that show up, they're almost exclusively going to be, at least first order, weight 1 or 2. You have local interactions, local errors. We don't typically have in physics many body interactions. And so you can reduce the experiment size accordingly as well. Say, I don't need to worry about, in say, a 5-qubit system, worrying about weight 4 errors. Yes. That's a good question, and I think in general, no. So what can happen is you can get, effective higher weight errors, right? Because you have some exponentiated low weight thing, and then the higher order terms will give you, right? Yeah, absolutely. So good question. So in order to sort of explain the dynamics of the full system, you say I want to write out what the error generator is for the full circuit, you'd have to consider those higher weight errors. But because those are computed directly from the error generators for each individual gate, once you've got the weight 1 and weight 2 errors, and then you multiply those out together, what will fall out are the higher weight errors that then impact the outcome probabilities for some longer circuit.
Okay, so it means that you're directly characterizing small components. That's
exactly right. Or just the button pushes, right? So the individual gate operations that we perform. So these are some things that we've been thinking about. One of the things that we're very interested in thinking about now is characterization in the fault-tolerant era, particularly GST in the fault-tolerant era. We now have platforms that can perform mid-circuit measurements and parity checks. So we've done a fair amount of work understanding how to tomograph mid-circuit measurements and parity checks. And then we're also wondering, well, now that we've got logical qubits that are extant in some sense, can we do GST on logical qubits? I'll put a couple of question marks there because there's a question of, does it even make sense? Does it even make sense to consider Markovian models for logical qubits? So one of the big open questions we're spending a lot of time thinking about. And then, of course, as I mentioned, there's lots of other QCVV out there that does not involve gates of tomography, with things like robust phase estimation. I don't know how many of you here knew Shelby Kimmel. She was a Hartree fellow here some years ago. It was one of her protocols, randomized benchmarking, which I'm sure many of you are familiar with. And of course, there are a whole bunch of other ones as well. So anyhow, just to wrap things up, we have a nice framework, broadly speaking, to improve and understand the performance of quantum computing hardware, and GST is just one of many tools that we've got. Lots of open questions that are still extant, particularly as we move to the fault-tolerant era, and we're always looking for new collaborators, graduate students, postdocs. Here is our website. Here's my email. As Victor mentioned, I live in the area. I'm in Heights, about 3 miles down the road, so hope to see more of you in the future. Thank you for your time. I'm happy to take questions.